Now we're going to start talking about free body diagrams of different forms. Today we'll talk about free body diagrams at single points. Next time we'll keep looking at free body diagrams, but we'll do a little more with equilibrium. Then next week we'll look at free body diagrams of rigid bodies, in other words beams. And then later we'll look at what if those beams have distributed loads, like flooring. Remember what we know about equilibrium, that for every action there's an equal and opposite reaction. And that means that we have three equilibrium equations in our toolbox. And the forces in every direction equal zero, and the moments in every direction equal zero. So drawing a free body diagram is a very important step when you're figuring out problems in statics, when you're working on structures. And today we're talking about a free body diagram at a particle. Sorry for that word use. This is our book explaining that particle just means 1 point. So don't worry about particle. We're talking about a free body diagram at 1 point. A free body diagram is not a picture, it's a diagram. And it shows the body pulled free of everything else. All by itself, it's isolated. Notice the word free, that's key here. We're pulling it free from everything. So here's a weight hanging from a ceiling. Here's the free body diagram. No ceiling, just the weight and the equal and opposite reaction. Here's our friend Shirley hanging from a ceiling. Here's the free body diagram of Shirley with the weight and the equal and opposite reaction. Here's somebody pulling on a rope, lifting a weight over a pulley. So you could make a free body diagram of 3 different pieces of that if you wanted to. Let's look at this first example and how we would tackle this. Here's a 100-pound weight hanging from 2 ropes that are screw-eyed into a wall and a ceiling. And at first you might think, oh, horrors, what are we going to do about the wall and the ceiling? No problem, because we're going to do a free body diagram at that 1 point. And we are going to use our analysis tool. This thing right here, this, I'm not sure what he's looking at, but imagine this is a paper towel tube. You imagine yourself looking through a tube at just one joint. And when you do that, you can't see anything around here. You can't see the ceiling, you can't see the wall, you can't see that weight. All you can see through your tube is that joint right there. So you isolate that joint and you draw a free body diagram for just that one joint. And because the weight is pulling down, that's in tension, so we have an arrow pulling away. And each of those 2 ropes is in tension, so they are pulling away. So we have 3 arrows all pulling away. And in CAD, you can draw that 100-pound arrow, 100 things long. We know about that. The others, we don't know how long they are, but we know what angle they're at, and we can arrange them tip to tail. And in a minute, I'm going to show you that in CAD. And this goes with the first problem in our assignment, where he says you've got 2 bars pinned together here at C, and then there's a force pulling away there. Determine the forces in these 2 members by isolating joint C. All right, first of all, this is a metric problem. You might notice he's talking about newtons. So here's a 500 Newton force, and we've got 2 bars here that are bolted to these ears, these pinned connections. At the bottom of the slide, I've given you the answers you should come up with. So check your work against these. You might be off slightly, but if you're in the general ballpark, that will be good. So what you want to do is get your imaginary paper towel tube and focus in on that one joint. Just look at that one. Don't think about these ears down here. You don't need them. You just need that joint at C. And what have we got when we draw a free body diagram? Well, we've got a force in tension pulling away. That's that 500 Newton force. Now think about what direction do you think these others are acting? This might take a little bit of thinking, but imagine this is your arm, let's say. And if your arm is that, and you've got a cable over here pulling that way, would your arm be feeling tension or compression? It would probably be feeling like something was pulling on it. It would probably be tension. So you draw an arrow pulling away. What about that third bar in the middle? If you have two forces pulling downward on either side, what is that bar in the middle feeling? And what if that bar were your arm? And what would your arm be feeling? Probably you are feeling some pushing, some compression. So you would draw an arrow for that bar pointing towards the joint. You got two in tension, so they're pulling away. And you've got one in compression, so it's pushing towards. Also, something else to think about is that the sum of all forces in all directions add up to 0. And right now, with these two tension forces, the y components of those forces are both in the down direction. So if this joint is in equilibrium, this other force has to be in the up direction, otherwise it'll fall apart. You can draw one arrow 500 things long, and you know it's at a 20-degree angle. The other two, you don't know how long to make them, so you just draw them a big old long length, but you can draw them at the right angle and arrange them tip to tail. And however long, measure where these intersect, however long that section is, that's the magnitude of that force. It should be what? BC, this should be 672. However long this one is, that's the magnitude of that force. That should be 768. So let's go look at an example in CAD. So this is the practice problem. This is this practice problem that we were looking at here. Example 1. So it's a 100-pound weight and two ropes at a 45-degree angle and a 30-degree angle, but who knows how long those were. Oops. So what I drew here is I've got an arrow. I made it 100 things long. I'm feeling cool because I got all fancy with my arrow. I made a nice even looking arrow with a polyline, so I hope you're impressed. I'm going to measure the length of that arrow just to show you that it is 100 things long. I'm up here in the utilities with the measure command. I use DI for distance, or I click that thing, and going from that endpoint to that endpoint, there's the report. Yes, the distance is 100 things long, so that's the right length. And I'm going to leave my free body diagram as it is, so in case I mess up, I don't have to start over. I can come back to this. So what I will do is I will make a copy of my 100-pound arrow here. I will move it over here somewhere. All right. Now I want to move these other two tip to tail. Well, which one should I put where? It doesn't matter. All that matters is the tail of one has to hook onto the tip of the other. You can't have two tails together, and you can't have two tips together. So I guess I'll just copy this one. And when I copy it, I can't just grab it out here in the air. Oops, copy. Let me try that again. What I'm trying to prove is don't do this. So select object, select base point. Oh, what the heck. I'll just click there. Oh, wait. That's no good because now I don't have a tip or a tail to snap to. So don't just grab it any old place. Let me try that again. Copy. I'm going to click my arrow, enter. I'm going to stick the tail of this one onto the tip of this one, so I will use that tail, that end point, as my copy base point. And I will drag my arrow over here. There. Yay! Now I'm going to copy this arrow, and I intend, I don't know how long this force is, but I do know that these guys have to go around in a circle tip to tail. So I'm going to put this tip next to that tail. So when I copy this one, enter, and it says specify base point, I'm going to grab this tip endpoint for my base point. And now I can move it over here and snap it onto that tail. And now, how long are these? Well, I can, oh, you know what I didn't plan for? I didn't plan for setting the text height in my dimension. This will probably be bad, but I'll try it. So I can get an aligned dimension and measure, oh, look at, yay me. So in this practice example, that 145-degree force is 90.19 pounds. And I'll get another aligned dimension, and the magnitude of that 30-degree force is 73.205 pounds. And now I might get some text. I might just get some text here and be cool and copy this over here, and I might go 90.190 pounds, and then I can delete my dimension. You can use the dimension. I'm just saying that having this clean looking magnitude is not a bad thing either. So I'll make this 73.205 pounds, enter, and then I can delete this dimension. And now I rather like that. It's a nice clean looking layout. You're welcome to use aligned dimensions though if you prefer. And one more thing, if I didn't want to use aligned dimension, I could use this distance command again, distance. And what I'm going to do is just type DI for distance, because I'm a typing person. And now it wants me to just specify the 2 points. One there, and one at that intersection. And look what it has given me. I'm a little bit off, so I'm not at 90.19, which tells me that I've done something wrong from there to that intersection. Yeah, I did something wrong when I put my dimension up here. So this proves that it's a good idea to check your answer 2 different methods. I'm not off by a lot, but I'm off, and so I need to figure out what I did wrong. Probably involves an O-snap. Okay, now we'll go back and we'll look at the second problem.